All right. So, covalent bonds are going to have a little bit of ionic character because we have charge separation, but not a we have a charge distribution. Charge, it's not really a separation. Okay, so anything that is 50% or more ionic character is considered ionic. So we have a continuum. You can use a rainbow as a good analogy, and they do some diagrams in the book that show that. So if it conducts electricity in an aqueous solution, it's considered ionic. So a covalent chemical bond compound forms if it releases energy to be formed, if the compound has less energy than the individual atoms. So carbon tetra, well, methane, carbon tetrahydride, I suppose we could have called it that. There's a two-dimensional representation of it. Bonds are just a model that people created to help look at things. But we can apply the same pieces to different compounds, so it's very helpful. So if it takes 1,652 kilojoules to break apart all of this compound, they can figure out that it's 413 per bond, and if it's that per carbon-hydrogen bond in this compound, it would be in other compounds as well. So we can look up bond energies. The ones in charts are averages. But here's some general things. A single bond takes 2 electrons, and it has the lowest energy and the longest bond length. A double bond has 4 electrons shared between them, so it has higher energy than a single bond and a shorter bond length than a single bond. But a triple bond has 6 electrons, so it has the highest energy of the 3 and the shortest bond length of the 3. And we can calculate the energy to break a bond or in a reaction with this equation. So if we look at this, H2 plus Cl2 equals 2HCl. Well, we need to know what type of bonds we have, and we have just single bonds in all of these. So, energy to break bonds. Well, these need to break so that we can make new bonds. So in order to figure this out, we need a chart because we have to look up the energy that is required to do these. So we consult a table, and like delta H of our reaction is going to be the sum of the energy to break the bonds. It's going to take 432 to break the hydrogen-hydrogen, and $239 to break the chlorine to chlorine, and then we're going to subtract from that twice the hydrogen chloride bond, which is 427. So now we just do the math. So this is 671. This is 854. So we get that the delta H, the change of enthalpy for this reaction, is this, which means it's exothermic, which means chances are this will happen spontaneously.